Hi, it's Dr. Hanson again. I hope you do feel as if these videos are helping you to zoom in and to get a better understanding of how the nomenclature of biochemistry works. And now I want to look at acids and bases. The good news is that this is something that you've worked through in freshman chemistry, and then you work through it again in organic chemistry, and you probably have done problems related to this in biology and maybe biochemistry. So you all have studied to some extent what pH means, what a pKa is, how weak acids and weak bases can be buffers, and most of you have at least heard of the Henderson-Hasselbalch equation, although you probably don't like it. I'm not here to teach a lot of freshman or organic chemistry. I'm here to zoom in on what really matters. And pH does matter, pKa matters, and even the Henderson-Hasselbalch equation is going to be used when you look at various types of respiratory or metabolic acidosis or alkalosis. So you do want to have a working knowledge of pH. And because there's some algebra here and a little bit of understanding of logarithms and exponents, this is the one part I think that a lot of people have the most trouble with. Certainly, I expect about a third of you to say, hey, I know all this stuff, no big deal. In that case, you'll be able to work through it quite quickly, won't take too much of your time. But I also believe that quite a few of you will struggle in this. And so again, I want to remind you, I am available to help. I want you to phone me. I want you to email me. I don't want you struggling for hours agonizing over this. I believe that 90% of what I say you're going to understand, but different people will get stuck on different parts. It's that 10% of the material that you're going to spend 90% of your time on. That's why it's so important to seek help. It isn't just that you're going to save a lot of time and get through it more quickly. It's also that you'll have a deeper and more complete understanding of it. And I think if you call me, you'll say, oh, is that all there is to this? A lot of these are very simple concepts that if you get it, then the whole picture makes sense. So do make it a point to talk with me if you get stuck, if you have trouble. Don't spend hours agonizing over this stuff. As a physician, should you have a working knowledge of pH and why? Please pause and answer. Absolutely, as a working physician, you'll have to have a basic understanding of what pH is and how it works. Human life is possible only in a condition of extreme tight regulation of blood pH. Along those lines, what is the average pH value of normal blood? And how much can it vary before you get sick and before you die? These are values that as a physician you will know cold, I guarantee it. In fact, the human body controls pH stringently within 0.1 pH units. The pH of a healthy person's blood will be very close to 7.4. It will be between 7.35 and 7.45. As a scientist in the laboratory, I might have some trouble controlling pH within such a narrow range. If your blood pH is not between 7.35 and 7.45, you will feel sick. And in fact, if you have a higher pH, you'll suffer from alkalosis or base sickness. If your pH is below 7.35, you'll suffer from acidosis or acid sickness. And for that matter, if your pH is not within a single pH unit between 6.8 and 7.8, you'll most likely die. It's remarkable how precisely our body regulates its pH. pH is pretty clinically relevant. Why is it so important to control the pH of your blood? Your body depends upon thousands of enzymes in order to run the processes of life. Each of these enzymes has a very narrow range of pH in which they will remain correctly folded and in which they will have the correct level of activity. For example, pepsin is a digestive enzyme in the stomach, and it's optimized to be functional between a pH unit of 1 and 2, because the stomach is acidic. Salivary amylase is a digestive enzyme in your mouth, and it is only active at a pH of about 6. Alkaline phosphatase is only active at a pH of about 9. If you do not maintain your blood at a pH of 7.4, then the structure of the proteins in your blood, their activity, the binding of oxygen to hemoglobin, all sorts of things will be altered, such that in the case of going to high pHs, alkalosis or base sickness, you can have cardiac arrhythmias, respiratory tetany, they can kill you. Alternatively, if you look in the other direction and you become too acidotic, acid sickness, then you can go into a coma and die from failure of the nervous system. Yes, pH is important. Here I'm showing you a plot of pH versus bicarbonate concentration. The physicians and physiologists will test you on many concepts using this exact figure related to acidemia, alkalemia, metabolic acidosis, metabolic alkalosis, respiratory acidosis, respiratory alkalosis, and this will be during cardiopulmonary during the first semester you're at A.T. Still University. I am pretty certain that quite a few students use brute force to memorize this plot without really understanding it. However, it is a lot easier to understand this plot if you have a basic working knowledge of pH, and if you have some idea of how buffering works. In order to get through medical school, I am certain that a lot of students have to memorize a lot of things, and they probably have to memorize too many things. The more you understand and do not have to memorize, the more your mind is freed up to memorize those things which you don't have a choice. And that's one reason I'm giving this video. Finally, I'm going to look at how different pharmaceuticals are soluble, how they're absorbed, how they're transported at different pH values. You will need to be able to use the Henderson-Hasselbalch equation, and if you understand the Henderson-Hasselbalch equation, it's a lot easier to use it. So what I want to do right now is slow down to be sure you have this basic understanding of pH so that you can work with it. What does pH mean? If you have a solution at a pH of 7, what is the proton concentration in terms of molarity? Please pause the video and answer. I'm sure some of you are saying, sorry, Dr. Hansen, this is too simple.
I'm also certain that others of you will be thinking, wow, I haven't even thought about pH in its fundamental definition since I was a freshman 4 years ago. That is a fundamental purpose in this preview video, to remind you of these very basic concepts, which really you should absolutely know cold.
The simplest thing to say is, if the pH is 7, you simply take the value 7 and make it the negative exponent of 10. That is, the proton concentration at a pH of 7 is 10 to the negative 7 molar. And it really has to do with what the basic definition of pH is, and it's simply a way of avoiding writing 0.0000001 molar. That is 1, 2, 3, 4, 5, 6, 7 decimal places to the right of the decimal point. Here's some basic definitions you absolutely will need to know to understand any biochemical conversation at medical school. Another requirement for any physician is that you be familiar with the metric system. I won't go far with it, but absolutely you need to know how molarity compares to millimolar, compares to micromolar, and compares to nanomolar. I will be using the word nanomolar quite a bit. So will the physiologist. I won't require that you know picomolar or femtomolar, but that much metric you have to know. Just to be painfully clear on that, 1 molar would be 10 to the 0 molar. 1 millimolar is 10 to the negative 3, or 0.001, 1 divided by 1,000.
1 micromolar is 1 divided by a million, and 1 nanomolar is 1 divided by a billion. Of course, the formal definition of pH is that it is equal to the negative log of the proton concentration. That is equivalent to saying you can take the pH value, say 7, and use it as a negative exponent of 10, because logarithms and exponents are inverse functions. And in fact, will you use a little bit of math to formally solve for what the proton concentration is if the pH is 7? Take a little stab at that. It's going to help you, I think, when we get to Henderson-Hasselbalch in terms of thinking about how these values work. But I'm going to move on. As I've already mentioned, logarithms and exponents are inverse functions. So we've just said that the pH of 7 is the negative log of the proton concentration. So we multiply both sides of the equation by -1 to get -7 is equal to the log of the proton concentration. Then we use each side of the equation as an exponent of 10. We're doing the same things to both sides. If -7 equals log of protons, then 10 to the -7 equals 10 to the log of the proton concentration. And of course, the exponential of 10 can also be called the antilog or inverse log. You can call it either way. So 10 to the log proton or the antilog of the log of protons is simply the proton concentration. Therefore, 10 to the -7 equals the proton concentration. A little bit of maybe trivial arithmetic there, but I think it will help you some when you get to the pH workshop. I want to go a step further because one thing that I notice every year is a number of students get test questions wrong on pH because they do the obvious thing. In your mind, you think, oh, if the proton concentration goes up, that means the pH goes up. We tend to think in terms of correlations rather than inverse correlations. So just be sure you remember the pH and the proton concentration are inversely related because it's the negative log. That means if the proton concentration increases, the pH decreases. If the proton concentration decreases, the pH increases. People just do that flip in their minds sometimes. It's something to keep in mind. We've already said what the proton concentration is at a pH of 7. In your mind, will you do a pH of 5 and a pH of 0? Just a very quick review, and then we'll move on. I like you to be able to think in terms of whole unit logarithms and exponents, but as we mentioned, the pH of blood is 7.4, which means the proton concentration is 10 to the -7.4 molar. And that's a little awkward to use. On a test, I don't want you to grab a calculator and hit buttons without understanding them. But right now, can you pause the video and tell me what type of metric units you would use to approximate that? Would this be some type of nanomolar, micromolar, millimolar? 10 to the -7.4. What's it between? Take a stab at that. Well, certainly 10 to the -7.4 is between 10 to the -8 and 10 to the -7. Please put in the greater than or less than signs. And again, the bigger the negative exponent, the smaller the number, so that 10 to the -7.4 is larger than 10 to the -8 and smaller than 10 to the -7. And that puts it between 10 to the -9 and 10 to the -6. What are the units 10 to the -9 molar, 10 to the -6 molar? Please pause and answer. You have to have some familiarity with these units. Little practice here. Well, 10 to the -9 is basically divided by a billion, which makes it nano. And 10 to the -6 is divided by a million, which makes it micro. So we have 1 nanomolar at 10 to the -9, 10 nanomolar at 10 to the -8, 100 nanomolar at 10 to the -7, and we can see that 10 to the -7.4 is between 10 nanomolar and 100 nanomolar. It's very close to 40 nanomolar. Again, this is to get you a feel of how to be thinking about exponents and logarithms in terms of some relatively simple math. And of course, if we're looking at pH values that might have some meaning to a physician, black coffee and beer are pretty important, slightly acidic, seawater slightly basic, blood barely basic, pH of 7.4, 40 nanomolar of protons, and of course you might be using a 1 molar strong acid or 1 molar strong base solution that would have a pH of 0 or of 14. And as we've been saying, the pH will be the negative exponent, or it can be written out much longer. Very simple to go between basically numbers and exponentials. This particular slide is not a learning objective. It's simply meant to show graphically how pH compares to the proton concentration. The physiologist will very likely show a graph of this nature. As the pH goes higher and higher and higher, that means the proton molarity will get smaller and smaller and smaller, so that all the proton concentrations are very tight against the line here, 10 to the negative 14, 10, 8, 6, 4, 2, 1. It's only when you get down near a pH of 1 that you begin to see a separation. So at a pH of 0, any exponent to the power of 0 is exactly 1. That's where you cross the axes. And for that matter, you could have a pH of negative 1, in which case that would be 10 to the negative negative 1, or 10 to the 1 molar, or 10 molar. It's a very frequently shown graph to try to give insight into that exponential relationship.
Just out of curiosity, how does the 40 nanomolar of protons in your blood compare to the amount of sodium, potassium, chloride? Is the proton concentration higher, or is the sodium, potassium, magnesium higher? Please answer. The physiologist will make a big deal about the concentrations of sodium and potassium in blood or in interstitial tissues versus the concentration intracellularly, where sodium is pumped out and potassium in. So they're kind of reverse between these. But if we look at the proton concentration compared to all of these other ions, we will find that the proton concentration is extremely low. Here again, we're listing it in millimolar rather than in nanomolar, and that's why there's not 7 decimal places here. How about the concentration of protons in a lysosome, which has a pH of 5? Can you give me the concentration of protons there? Well, it'll be 10 to the negative 5, or 0.01 millimolar, because a millimolar is 10 to the negative 3, 10 to the negative 4, 10 to the negative 5. Again, we're still dramatically lower than most of these other ions. How about in the stomach with a pH of 1? Can you tell me what the proton concentration would be there? Please calculate it. At a pH of 1, proton concentration will be 10 to the negative 1, which is 0.1 molar, or 100 millimolar. Now you notice in the stomach, the proton concentration is similar to a lot of salts. What is the ratio, say, of bicarbonate to proton? In the blood, it's about 1,000,000 to 1. And why does that matter? Bicarbonate acts as a buffer, meaning that if you add protons to blood, some of them will stick to the bicarbonate to make carbonic acid, and therefore they will be buffered. And the reason bicarbonate is such a good buffer is that it's a millionfold in excess over the typical concentration of protons. And right now I want to look at that. How you control the pH of your body. We'll make a much bigger deal of it in cardiopulmonary. But let's look at buffering, and I'm going to begin by looking at a strong acid. Let's say that we have a concentrated solution of hydrochloric acid and we dump it into a liter of water. And we add a total of 100 millimoles of hydrochloric acid. What will the proton concentration be, and what will the pH be? Will you calculate that quickly? These are the most basic understandings you'll need. Hydrochloric acid is a strong acid, which means the proton and the chloride completely dissociate. So if you add 100 millimoles of HCl,
you've added 100 millimoles of protons. That means in 1 liter there's 100 millimoles, which makes the concentration 100 millimolar in protons. What does that make the pH? Of course, pH is defined as the negative log of the proton concentration in molarity, not in millimolarity. So we have to look at what this is in molarity, which is 0.1, and we will take the negative log of 0.1. Please try to come up with that quickly, and I'll move on. The logarithm of 0.1 is negative 1, so the negative logarithm of 0.1 is 1. Now, I don't expect you to instantly be able to pull that out of your head, but just let me remind you, what's the logarithm of 100? Well, 10 squared is 100, so logarithm of 100 is 2. What's the logarithm of 10? 10 to the 1 is 10, so logarithm of 10 is 1. Logarithm of 1 is 0, because 10 to the 0 is 1. Anything to the power of 0 is 1. And the logarithm of 0.1, or of 1/10, is negative 1. In order to check whether or not the logarithm of 0.1 is 1, you absolutely need to understand that the anti-log function or the inverse log function is the exponential function. So we can say, does 1 equal the negative log of 0.1? We simply take the anti-log, or we use both sides of this equation as an exponent for 10. So 10 to the negative 1 molar is equal 10 to the base 10 log of 0.1. 10 to the log cancels. They do the inverse of each other, leaving you with 0.1 molar. So, in fact, that is the correct answer. Really good to have some feel for exponents in logarithms, but you don't need to be perfect with the arithmetic. Here we just dumped this strong acid in, and it instantly was dissociated and changed the pH. But what if we're not dumping that strong acid into water, but instead, let's say we inject it into some blood. Let's say we take a dog and we inject 150 millimolars of hydrochloric acid into his veins. And by the way, this was a real experiment, before all that government regulation. I think it was the 20s or 30s. But there was this guy, Robert Pitts, who did exactly that, and he noticed that it changed the pH. Is this what you would predict? If you're adding hydrochloric acid, would that cause the pH to go down? Please answer. A low pH means high protons. High pH means low protons. So the pH is inversely related to the proton concentration. And it's so easy to think, high pH, that must be high protons. But it's not. It's the complete opposite, because it's a negative log. So the point is the pH changed, but I would have predicted a bigger change. This is a lot of hydrochloric acid to add. Why was the dog still alive? Can you answer the question? What happened to those protons? And in fact, our blood has a lot of buffers, such as carbonic acid. And we also have protein in our blood, like hemoglobin, with histidine side chains that at fairly near physiological pH can accept or give up protons. And there's inorganic phosphate, which can give up or take protons. So now we've added the hydrochloric acid. The pH didn't change as much as we would have predicted. What happened to the protons? How does a buffer work? Please pause and answer and tell me where those protons went. Well, this is what's so neat about a buffer. If we have a millionfold carbonic acid over proton in the blood, that means that when you dump the protons in, they can stick to bicarbonate, the conjugate base, and convert it to carbonic acid. So this is Le Chatelier principle. You're adding hydrochloric acid. Some of the protons stick to bicarbonate to make carbonic acid. Some still float around to lower the pH. Some of them stick to histidine. Some of them stick to inorganic phosphate. And what's really neat about your blood is those proteins that need to work at a specific pH. If you have too many protons, their activity will be altered. But if you have too much carbonic acid or too much protonated inorganic phosphate, that has no effect on these proteins. So essentially, buffers remove the protons. Now, What if instead of adding hydrochloric acid, we add sodium hydroxide, a strong base that completely dissociates? We would predict the pH in the blood will go up because you're taking away protons. The proton concentration is going down, the pH goes up. But it won't go up as much as it would go up if you simply added those hydroxide ions to a bottle of water. Why? Because in this case, these hydroxide ions will grab the protons off of the acids and slightly perturb the conjugate acid conjugate base equilibrium. And again, it's very slight. There's so much buffer in your blood and usually so few protons exchanging. And this is going to be extremely important when we're talking about alkalosis in acidemia. I'm hoping this very simple review of freshman chemistry helped you think about mathematically what pH means and how buffers work. If there's any ambiguity in your understanding of logarithms and exponents of pH, please come and talk to me. Now I hope you'll go on to part 2 and learn a little bit about the Henderson-Hasselbalch equation, which in fact I hope you don't even rely on. Rather, please listen to my simplified description of how Henderson-Hasselbalch works and how you can avoid having to do a bunch of algebra.